All right, so found something, thought it was pretty interesting. Kind of went down a YouTube rabbit hole. You know how like we kind of go down rabbit holes on YouTube. We've come across something and then a video kind of piques our interest and then we look up other videos on that same topic. Uh I just wanted to talk about this and give my opinions on it because when I was a kid, I always thought that um when I found out about black holes, I always thought that like if black holes are like taking in matter, then probably the same thing's going on inside the black hole that is like going on outside the black hole, right? Like stars, planets, matter kind of comes together and makes stuff. Well, like if a black hole just keeps taking in matter, well, then why wouldn't stars and planets and stuff like that start forming inside that black hole from the matter that it's swallowing up? And I came across this Neil deGrasse Tyson, very handsome gentleman, very popular and very smart gentleman, astrophysicist. You probably have heard about him. Talks about um, some evidence that could be pointing to possibly our universe being in a black hole. And it kind of just talks about, I'm going to sum it up real quick, just do a brief, because this isn't even like the rabbit hole that I fell into. I'm afraid this video is going to go too long. But like, I just got my mind blown by a crazy rabbit hole that I fell into about black holes and gravity and stuff like that. um, but it kind of just talks about how like there's a rotation, like a general rotation that our entire universe has that's been detected. So really smart people that are way smarter than me kind of have identified the rotation as being like not normal. And it somehow ties into our universe being in a black hole because if the entire universe has like a general rotation, they now have to explain where that general rotation came from because the original idea was just like everything rotates cool and it's pretty much randomized. This is Neil talking about that.
Well, that was linked to the idea that we might be in a black hole. Here's why. There's only two kinds of information you can obtain that are preserved inside that black hole. The mass, the total mass, and the angular momentum.
So the rotation,
Is that
right?
an iPhone 17?
Switch to T-Mobile in just 15 minutes.
You get a new iPhone 17 on them with its awesome camera, and they'll even deliver it the same day.
Switch to T-Mobile in just 15 minutes. Get a new iPhone 17 on us with same-day delivery.
Why am I wearing a tutu?
Because anything falling in, if it falls in with a swirl, toilet bowl style, that angular momentum continues into the black hole itself. If there's a net angular momentum of the universe, where did it come from? It's not obvious that would come from a Big Bang, which is an explosion in all directions statistically evenly. What could it be? Could we be a black hole with a net angular momentum of stuff that spiraled into us? So that's where the black hole connects back to whether the universe is rotating. So I look forward to seeing whether this result is confirmed or falsified.
So I kind of started like postulating like what would that mean, right? Like was I right when I was like 8 years old? There's like just black holes inside of black holes inside of black holes, and it's just like constant, like just universes everywhere. So it kind of just made me dive into like gravity and stuff like that, and then I came across this guy's video, really cool. And I was just kind of like brushing up on like how gravity and speed affect time differently. Like this one, like everyone knows, like the interstellar type of differences between like when they get close to a black hole, something that has a lot of gravity, time slows for them. A lot of people have a hard time wrapping their mind around it. And it kind of goes way deeper, I guess, and I wanted to talk about that. This is the part that blew my mind, but it's not that it blew my mind. in and of itself, it's that there's a like a diagram, like you can prove that this is what it is. Like there's a physical diagram that you can show, and it's this fact right here, which is just mind-blowing. Listen to what he says right here.
But remember, according to Einstein's model, there is no force of gravity at all. Nothing is pulling down on us. Then why does the apple fall down? Why do we feel our weight? Well, that's because Einstein says it's the ground that is instead accelerating up.
You got to be kidding me. Mind-blowing, right? So when we drop something, it's not being dropped. To our perspective, it looks like it's dropping, but it's not. The ground is coming up to meet it. So he addresses this. There's two good videos. You know, this guy, this is his channel. This is the first video, and this is the second video. So this is kind of like two-part video that I want to combine together real succinctly, really quickly. Forgive me if I take too long, but I just wanted to center focus on that fact that when objects fall, they're not falling. The earth is coming up. The ground is coming up to meet them. And I'm going to try and make this as dumbed down for me and everyone else who's dumb like me as possible. So he kind of talks about, well, like, you know, if that's the case, if the earth is coming up, well, then the earth is like a ball, right? A sphere. So if the ground is coming up, then the earth would be expanding, getting bigger. And Einstein says, no, not necessarily, because you're not taking into consideration the curvature of space-time. So us stupid people, we don't know what the hell that means. So I'm going to show you something fundamental that is important to understand what's going on here. So essentially, he provides a analogy that Einstein gives to show you that, hey, just because I'm saying that the ground is coming up to meet the apple that you dropped, doesn't mean that the earth has to be expanding. The ground can be coming up, but also, it can also be true that at the same time the ground is coming up, the earth is not expanding. And then he gives this example. So in this example, we have two objects that are rotating in a circle, right? And both of these objects are accelerating towards the center of the circle. So I'm not going to get into, you know, centripetal force and all that. Everybody can go look at that themselves, but take my word for it. In this model here, when things rotate, whichever way they're rotating, in this model I think they're rotating to the right, he has an arrow here with an A indicating acceleration towards the middle. So this block of dirt and this block of dirt, they're both spinning around in circles, and they're both getting accelerated to the middle. This is important because that is showing you that at all times, gravity is being, well, the effects of gravity are being mimicked, right? Like this person is going to stay against this patch of dirt because this patch of dirt accelerating into the circle is simulating gravity, so she feels like she's being pulled down. She feels like she's being pulled down onto the ground, but really it's this accelerating upwards. And if they're spinning here, due to the nature of this layout, you have one block accelerating towards another block. They're both accelerating towards the middle, but they're always staying the same length apart, right? Like if this rotates and this rotates all in this circle at the same time, they're never getting any closer together. This is never coming into the circle. This is never coming into the center. But they're both accelerating into the center while staying the same distance apart. Very important to note. Super cool. There's just one more thing that we really have to understand, and it's the effects of time. To get the diagram that he shows in the next video of how the ground really is accelerating up. And it's this right here. So let me see if I can't show you this little diagram he has. So he's going to remind us, this is pertinent to understand, it's pretty much just like time dilation, right? Everyone knows, or at least we don't know the finer details, but it's the fact that time slows down when something's moving very fast. So if something is moving super fast, time goes slower for that thing than it does for something that is not moving. Also, gravity. If something is closer to very strong gravity, time goes slower for that thing than something that doesn't have a lot of gravity acting on it. So he can show you that in this easy diagram.
Remember time dilation in special relativity? Moving clocks take slower compared to the clocks that are at rest. And an intuitive way to think about it is in terms of photon clocks. If you have a photon clock with you at rest, it'll keep ticking at the maximum speed. But if the same clock is moving, now the light has to travel a bigger distance.
So, pretty simple. You can see it. He's showing it to you, right? Like, if this was standing still, right now it's on wheels and it's moving. But if it was standing still like it was, the distance from here to there, it's just a line. The quickest path to something, a line, right? But because it's moving now, in order to get from here to there, it's actually traveling in space. It's going to be going this way. So by the time it gets to the top, look how much distance that is right there. Hope you can see my mouse. Look how much distance that is right there. That's a much further distance than just this right here, right? And it's just because it's moving. So because this could be moving the exact same speed, but because of this distance here, while it's moving, because that's further, it's going to take longer for this thing to get up here. Ergo, it's ticking slower. The faster you're going, so the faster that this thing is hauling butt this way, the more distance this little thing is going to have to cover, because it's going super fast this way, and it's going to be coming up at the same time. So the quicker, the faster you go, the less or the slower time is going to be affecting you. So then he shows you this here, super intuitive little design, where in the middle, let me see if he can explain it real quick.
Are outside, we are looking at this from far away. You can imagine we are at rest with respect to the center of this spaceship. Okay, now from our perspective, look, people over here are hardly moving. They're pretty much at rest. They're hardly moving, so their clocks are not dilated at all. Their clocks are ticking pretty much at the same rate as our clock. But look at the people over here. Oh my God, because they're moving so fast, much faster than people over here, their clocks will be dilated a lot more, and therefore their clocks will be ticking much slower than our clocks. So as we go farther and farther away, the clocks tick slower and slower. Again,
Okay. So obviously, it's spinning at the exact same rate, right? The people in the middle, like he said, there's not a lot of distance, but it's spinning at the same rate. But look at the distance of this circle. The distance of how long this circle is, it's not that much. So, but look at the distance of this circle. It's pretty big, right? So if it's spinning at the same rate, except this dot is covering way less distance, while this dot is covering massive amounts of distance, more than this one. So obviously, with deductive reasoning, if you cover more space in the same amount of time, you're going faster, right? If you're going 1 mile every minute, you're not going as fast as if you were going 2 miles in 1 minute. So the more distance you cover in the same amount of time, you're going faster. So the same amount of time, this thing's going 1 rotation here, while this thing is going a huge rotation, covering a whole bunch of distance. So this outside is going faster, which intuitively means that time, as we saw, is going to be going slower. because, well, you saw the diagram. So we're going to correlate the speed with also gravitational effects or perceived gravitational effects. The people here in the middle, although they're spinning at relatively, same rate, the same rate really, they're not covering so much distance. So when they are spinning, when they're spinning, these people out here are going to have more gravity. It's going to feel like they're getting pulled down onto the floor. Their gravity is going to be a lot higher than in the middle. The people in the middle are not going to have as strong gravity, and the further you go out, the stronger the gravity is. So that directly correlates with, like, this is going faster. You're going faster, so time will go slower for you. Also, just like if you get closer to a supermassive black hole, you are getting closer to higher levels of gravity, time slows down for you. So here we have both examples pretty succinctly that the outside, that's where you feel the most gravity, time is slower. The outside is where you're going the fastest, time is slower. Okay, two birds, one stone. So this is a pretty interesting. We're going to come back to this part. I want to show you guys this part because this goes hand in hand with his next video that literally shows you how the ground is coming up.
To the right with a constant velocity, because remember, there are no forces over here. There's no gravity, there's no planets, there's nothing, right? So if you let go of an apple, it should go to the right. But at the same time, this whole patch of space and this whole patch of ground curves upwards. So see what happens as the apple goes to the right. Eventually it'll be blocked by.
So we know that this block is accelerating towards the middle. That's why it feels like she's being pulled down. This apple is also traveling. If you're sitting on this block and everything that you are with is sitting on this block, all of you are going in the same direction as this block. So when you drop the apple and you leave it suspended, the apple is going in the same direction as this block was going when you last let it go. So the block was going this way, right? Following this curve. You drop the apple here, so the apple's going this way. Look what happens. The apple runs into the moving block. The apple is just going exactly where it was always going to go. The block is what is moving to meet the apple. Just like the block is accelerating inward to meet the person, to provide some sense of artificial gravity. Now, I'm going to come back to this because it's extremely similar to what he's going to show next. Blew my mind. Very succinct way of showing that the ground, it's hard to fathom. The ground is coming up. Nothing is falling. Mind-blowing. So here he puts a diagram, right? Space-time diagram. This is time, and this is space. Pretty simple. So what he does is he puts an apple here. Now he represents this apple as not moving. We know that whenever something goes faster, time is slower on it. So he makes this apple not move in space, so it's not going to be going this way at all. It's just going to be moving in time, right? So that's what happens. Each one of these arrows, he decides to make, a second. So we have the apple not moving, just completely stationary, not moving in space, and 1 second goes by, 2, 3, 4, 5 seconds go by. And then he does this with a blue apple. The blue apple's moving through space. Blue apple's going pretty freaking fast too, because this blue apple is checking their watch as they're moving really fast through space, and the blue apple times that it's been moving 1, 2, 3, 4, 5 seconds. Well, looky here. 5 seconds here to this blue apple is only 3 seconds here to this stationary apple. How interesting. So time has affected, 5 seconds has affected this stationary apple much more than 5 seconds affecting this moving apple. So again, just a visual diagram of showing how speed can reduce the effects of time on an object, you know. Okay. Then he does something interesting here. Then he rolls the paper up. Now he's getting closer to the answer, right? Now when he rolls the paper up, we have to remember that this line is 5 seconds, okay, for the stationary apple. We also have to remember that this blue line is also 5 seconds to the blue apple. If the stationary apple was timing 5 seconds, hey, 5 seconds went by, okay. And then the blue apple's hauling butt, he times for 5 seconds. Then the blue apple's going to say, hey, bro, 5 seconds went by right here. But that's not the case. Because the other apple is going to say, oh, hell.
This holiday season,
T has remained the same.
Because the other apple, the stationary one, is going to be saying, bro, what do you mean 5 seconds? It's only been 3 seconds. The blue apple's going to say, no, bro, I just timed 5 seconds. And we can see that when he rolls the paper and we see that this apple here actually made it to the whole 5 seconds. But look what 5 seconds is to this apple. Hasn't even got to the 5-second mark yet. Because of how fast it was moving. Time affected it. Time had less of an effect on it. So we know that an entire roll here would be considered 5 seconds. From the start of this dot, when something comes around, that's the time frame. He rolled the paper up. One rotation is 5 seconds. Check this out. Then he puts 2 apples. They're stationary, right? They're not moving to the right. The attribute that he's put on them is one's over here in space, not moving. One is over here in space, not moving. However, now instead of speed, instead of velocity, he's introducing mass. So this is the Earth, right? This is what he's saying. This patch of dirt over here is the Earth, and we know that not only does speed affect the effects of time on an object, but gravity, the perceived gravity, also, if you get closer to something that's super gravitationally strong, you're going to have less of an effect. Time will move slower for you the closer you go to gravity. So in this case, these 2 apples are both stationary, but one is closer to a big gravitational object, and one is farther from a big gravitational object. So we know that this is wrong, right? We know that we can see how speed is affecting the time. The faster you go, the slower time moves for you. But what about this? How do we make this consistent with gravity's effect on time? Because if this roll of paper right here is 5 seconds from this point all the way around, but this apple is closer to a big gravitational mass, and this apple is further from a big gravitational mass, then they cannot reach the 5-second interval at the same time. Time is going to be moving slower for the thing that is closer to that big gravitational mass. So how do we fix this? Well, he explains, and it's amazing.
One, and yet make sure it hasn't finished the full circle. How can you modify this diagram to incorporate that? There's only one way to do this. We have to have a bigger cylinder over here. Think of
So that is what you have to do. You'd have to modify the diagram so that way this apple has to go further in time in order to reach the 5-second mark. Because the closer you get to a gravitational mass, the slower time affects you. So then the three-dimensional model of this is nuts. I love it. Check it out. So what he does, because it's a gradual increase, right? Like gravity just doesn't immediately begin bigger over here. No, it's the closer you get to gravity, gravitational force is increasing. The gravitational effect on you is gradually getting more and more and more. So time is dilating more and more and more. It's kind of like a cone. Now, what does this look like when you open it up? This is what blew my mind. So, we have here, right, our original little diagram of space and time, right here, right? That's space, and that's time. So remember, if we wanted to put an object in here, if it's moving through space, it's also going to be moving in time because time is going by, right? Time, to our perspective, time is linear. And we'd be going forward in space. This would be movement wherever it's going to be. So space and time are affected by this he has labeled as ground, right? The ground here is mass. It's the earth. So the mass, something that is really massive that creates a lot of gravity, is affecting space and time. It causes this crazy curve right here. This is a very accurate three-dimensional diagram that shows you right here, get ready to get your mind blown, exactly how the earth can come up to meet the apple that you drop. The apple's not falling, the ground is coming up to meet it. So here he draws the apple. This dot represents the apple that is stationary. It's not moving. Because remember, this bottom line here is space. So if the apple was mobile, going real fast, it would be traveling in space this way. The more it comes this way, the faster it's traveling. And then as time goes on, it's going this way. It's gonna, time's curved. It's going this way. Such a beautiful. My mind's still blown about this. Check this out. Look what happens if the apple is not moving in space, so it's not going this way. It's stationary, so it's moving in time, and it has to go straight, right? Well, because time and the gravitational mass is affecting time and space in such a way that it curves it, look what happens when the apple stays stationary.
to move through time only. It'll go like this. It should continue straight line. This is how it will go. So this is what's happening according to Einstein. And now let us see what happens in our spatial and temporal terms as we see it. As we see it, what do we notice? We see the apple falling to the ground.
Genius. Amazing. Mind-blowing. So from our perspective, we see the apple falls to the ground. The ground doesn't come up because we don't perceive the ground to be doing that. But it is. Space, time has been warped so much by what? By mass, by the huge mass of the Earth, that the appearance of gravity is the apple falling. Apple doesn't fall. Does this look familiar? Yes, it does. It looks almost exactly like the example that Einstein gave us of
space and this whole patch of ground curves upwards. So see what happens as the apple goes to the right, eventually it'll be blocked by the ground. And so notice from her perspective, it just feels like the apple fell down.
similarly as you can have these two rotating masses right directly across from each other, rotating in this circle at the same speed. They can both be accelerating towards the center here. This patch of grass and this patch of grass are both accelerating inwards, but they're never getting any closer to each other. Similarly, as that's possible, you can have a huge mass that is affecting space and time to make it seem like there is a force called gravity, but the only thing that's happening is there is no gravity. It's just a huge mass is affecting space and time. Gravity is just something we call the symptom of a huge piece of mass, whether it be something really heavy, right? A huge piece of mass, what it does to space-time. It's gravity is literally just a symptom of mass and energy, or velocity. Mind-blowing. So there it is. Yeah. Proof through a very reliable and succinct three-dimensional model that the apple's not falling. The Earth is simply accelerating upwards to meet the apple, and that's happening in all directions on all sides of the Earth at all times. Super hard to conceptualize if you're thinking of like basic observations, but when you realize that space-time is warped around the entire planet evenly in all directions, that's happening at every point. It's fascinating to me. So essentially, he kind of goes into like what Newton thought and what Einstein thought, which is super cool too.
It's going in a curve, accelerating down. But then because we see ground to be at rest and apple accelerating down, Newton thought, well, that's basically what's happening. The ground is at rest and the apple is accelerating. But then because of all the discussion that we thought, Einstein realized maybe that's not the case. Maybe it's the ground that is accelerating up and the apple stays put. The equivalence principle. Now, when the moment we do that, this is how we start thinking about it, right? And as a result, we start wondering, well, if that is the case, then why doesn't the ground, if the ground is moving upwards, the ground is accelerating upwards, then shouldn't the earth expand? Well, the problem is this is not the right way to think about it because you haven't considered the curvature of time, which is important if you're using Einstein's theory. But when you do
Right, so again, the ground is a huge piece of mass. You're not interpreting how that mass is affecting space-time. We know that large pieces of mass affect space-time. So you have to incorporate that into the diagram, which is what is happening here, and it's beautiful.
incorporate it, you'd actually see that yes, ground can accelerate up.
So here, the mass that is curved, right, is now aptly being represented as changing, curving, messing with space and time.
The apple is inertial, but when you see it in the ordinary spatial and temporal terms, notice Ground is not moving anywhere. It just stays put.
Right, and that's how we view it, right? This is how we would see it. From this perspective, all we see is a triangle, two-dimensional. We don't see the three-dimensional object. It's just triangle, right? Boom, boom, boom. To us, the ground is a constant. Ground's not moving. To us, space is not moving this apple. This apple is not mobile only until you let it go and it drops. Well, what happens as time here, as time goes by? Well, the apple gets closer to the ground, giving the appearance that the apple is what is moving. But it's not. It is the ground. It is the ground right here. Come on. Come on. Come on. It is the ground that moves to meet the apple. Except reverse, right? Like this is, yeah. I hope you guys get it. Super cool. Mind blown. I hope I helped.